Richard Feynman here, and I want to talk to you about something that has kept physicists awake at night for over a century. Something so strange, so deeply unsettling, that even the people who figured it out weren't sure what to do with it. Time. You think you understand time. You live inside it. You feel it moving. Right now, as you watch this, you feel yourself being carried forward from this moment to the next like a river pulling you downstream. The past is gone. The present is here. The future hasn't happened yet. That feeling is so fundamental, so built into what it means to be a conscious human being, that questioning it seems almost ridiculous. But here's what I've learned from a lifetime of doing physics, and this is something I want you to really hear. The universe does not care what feels obvious to you. And when we actually look at the equations, when we do the experiments, when we follow the mathematics wherever it leads without flinching, time becomes one of the most bizarre, most confusing, most philosophically explosive things in all of science. So let me ask you the question seriously, not as a thought experiment, not as science fiction, but as a genuine, open, unresolved problem in fundamental physics. What if time isn't real? What if the flowing, ticking, forward-marching river that you experience every moment of your life is not a feature of the universe, but a feature of you? Let's start from the beginning, and I mean the real beginning, not with clocks and calendars, but with physics. In the late 1600s, Isaac Newton gave us a picture of the universe that was extraordinarily successful. In Newton's universe, time is absolute. There is a single cosmic clock ticking somewhere, and it ticks the same for everyone, everywhere. Whether you're standing still or flying through space, whether you're on Earth or on the far side of the galaxy, 1 second for you is 1 second for me, is 1 second for everyone. This seemed so obviously correct that nobody questioned it for over 200 years. Then along comes a young patent clerk in Switzerland in 1905, and he blows the whole thing apart. Albert Einstein, and I say this with enormous admiration, had the audacity to take seriously something that the equations were telling us, even though it contradicted everything that felt intuitively true. And what the equations were telling him was this: there is no universal clock. There is no single now that applies to the whole universe. Time is not absolute. Time is relative. This is special relativity. And I want you to understand what this actually means, because people hear time is relative and they think it's just some abstract philosophical statement. It isn't. It's a concrete, measurable, experimentally verified physical fact. Here is the core of it. The speed of light, roughly 300 million meters per second, is the same for every observer, no matter how fast they're moving. That's the rule. That's the thing Einstein insisted on. And from that single insistence, everything else follows. If you are moving very fast relative to me, say close to the speed of light, then your clock runs slow compared to mine. Not because your clock is broken, not because something is wrong with your clock, but because time itself for you is genuinely ticking more slowly than time for me. This is called time dilation, and we have measured it. We put atomic clocks on airplanes and flew them around the world, and when they came back, they had ticked slightly differently from the clocks that stayed on the ground. We watch subatomic particles called muons, created in the upper atmosphere by cosmic rays, survive long enough to reach the Earth's surface, which they should not be able to do given how short their lifetimes are, except that they're traveling so fast that time for them is running slow, and so they last longer from our perspective. Time dilation is not a theory. It's not speculation. It happens. We've seen it, but here's where it gets even stranger. In special relativity, Einstein introduced the concept of space-time. Instead of thinking about space and time as two separate things, a three-dimensional arena that things move through in time, he said, no, they are one single four-dimensional fabric, space-time. And in this space-time, what counts as space and what counts as time depends on who's measuring. Two observers moving at different velocities will, in a very precise mathematical sense, disagree about which direction in space-time is the time direction and which directions are the space directions. Think about what this means. There is no universal now. Simultaneity, the idea that two events happen at the same time, is not an absolute fact. It's a relationship that depends on the observer. Two events that are simultaneous for me may not be simultaneous for you if you're moving relative to me. This is called the relativity of simultaneity. And it's not a paradox or a contradiction, it's just how the universe works. The universe doesn't come with a built-in present moment stamped on it. The present moment is something that observers have, not something the universe has. Now, take a breath, because we're just getting started. Einstein then spent the next 10 years working on an even bigger problem. What happens when you include gravity? And in 1915, he gave us general relativity. And in general relativity, time gets even weirder. In general relativity, gravity is not a force in the traditional sense. Gravity is the curvature of space-time. Massive objects, stars, planets, black holes, bend the fabric of space-time around them, and objects moving through that curved space-time follow the natural curved paths, which is what we call gravitational attraction. But here's the consequence for time. In curved space-time, time doesn't just dilate due to relative motion, it dilates due to gravity itself. The deeper you are in a gravitational field, the slower your time runs. This is gravitational time dilation, and again, we've measured it. The clocks on the GPS satellites orbiting Earth, which are in a slightly weaker gravitational field than we are on the surface, tick slightly faster than clocks on the ground. The GPS system actually has to correct for this effect. If it didn't, your GPS would accumulate an error of several kilometers per day. General relativity is not just theoretical physics for physicists to argue about. It's embedded in the technology in your pocket. Now, here's a beautiful and deeply strange consequence of general relativity that I want you to sit with. At a black hole, at the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite. From the perspective of a distant observer watching someone fall into a black hole, that person would appear to slow down, move more and more slowly, and asymptotically approach the event horizon, but never quite reach it, frozen in time as seen from far away. From the perspective of the person falling in, they fall right through. Nothing particularly dramatic happens at the horizon. They're gone. But from outside, they're frozen. They're stuck at that moment forever. Two radically different experiences of the same event. Both equally valid descriptions of what's happening from different reference frames. So already, just from special and general relativity, time is looking nothing like the simple, universal, ticking clock Newton gave us. It's personal, it's local, it's malleable. It bends, it stretches, it slows down and speeds up depending on where you are and how fast you're moving. But here's where I want to take you now, to a question that's been bothering physicists for decades. The equations of physics are, for the most part, time-symmetric. What does that mean? It means that if you take the laws of physics, Newton's laws, Maxwell's equations of electromagnetism, even the equations of general relativity and quantum mechanics, and you replace the time variable t with negative t, the equations still work. They're still valid. They describe perfectly physical situations. In other words, the fundamental laws of physics don't distinguish between forward and backward in time. Let me say that again because it's remarkable. If you filmed a collision between two billiard balls and played the film backward, there is nothing in the laws of physics that would tell you which version is the real one and which is the reversed one. Both are equally valid, equally physical solutions to Newton's equations. So here's the puzzle. If the laws of physics are time-symmetric, if they work equally well forward and backward, then why does time have a direction? Why does the past feel so different from the future? Why can we remember yesterday but not tomorrow? Why does a cup fall off a table and shatter, but a shattered cup never spontaneously reassembles itself and jumps back onto the table? This is called the problem of the arrow of time, and it is one of the deepest, most genuinely unsolved problems in all of physics. The standard answer, and this is the answer most physicists give, comes from thermodynamics, specifically from a quantity called entropy. Entropy is, loosely speaking, a measure of disorder. A cup is a low entropy state. All the molecules are arranged in a very specific, highly organized configuration. A shattered cup is a high entropy state. The molecules are spread out, disorganized, with many possible arrangements. The second law of thermodynamics says that entropy always increases, or at least stays the same, over time. The disorder of a closed system never spontaneously decreases, and this gives time its direction. The past is the direction of lower entropy. The future is the direction of higher entropy. Time flows from order toward disorder. But here's the thing, and this is what really bothers me about this answer. The second law of thermodynamics is itself ultimately derived from the underlying laws of physics, which are time-symmetric. So how do you get a time-asymmetric law from time-symmetric fundamental physics? The answer seems to be initial conditions. The universe, we believe, started in a state of extremely low entropy, and the Big Bang was a highly ordered, highly special, very low entropy state. And because everything started there, everything has been evolving in the direction of increasing entropy ever since. The arrow of time isn't in the laws of physics themselves. It's in the initial condition of the universe. But then you have to ask, why did the universe start in such a special, low entropy state? Why was the Big Bang so ordered? And there, we don't have a satisfying answer. We have hypotheses. We have speculations. We have mathematical frameworks. But no one can tell you from first principles why the universe began in a low entropy state rather than a high entropy one. Which means the arrow of time, the very thing that makes your experience of reality feel the way it does, the fact that you remember the past and not the future, the fact that causes precede effects, the fact that you are aging rather than getting younger, may ultimately rest on a single, unexplained, lucky initial condition of the universe. That's a bit unsettling, isn't it? Now let me take you somewhere even more radical. In the 1960s, two physicists, Bryce DeWitt and John Wheeler, were trying to do something enormously ambitious. They were trying to combine general relativity with quantum mechanics, trying to write down an equation that described the quantum state of the entire universe, gravity and all. They arrived at an equation now called the Wheeler-DeWitt equation, and it has a very strange property. Time doesn't appear in it. I don't mean time appears in a weird form or time is hard to identify in the equation. I mean, there is no time variable. The equation is completely timeless. The universal wave function it describes, the quantum state of the whole universe, doesn't evolve in time because there is no external time for it to evolve in. In ordinary quantum mechanics, systems evolve in time. You have a quantum state, and it changes according to the Schrödinger equation, which explicitly contains a time variable. But that works because you have an observer outside the system measuring things, and that observer has a clock, and things evolve relative to that clock. But when your system is the entire universe, there is no outside. There is no external observer with a clock. There is nothing for the universe to evolve relative to. And so, time disappears. This is called the problem of time in quantum gravity, and it's not a technicality. It's not an artifact of how the equation is written. It's a deep conceptual problem that suggests something profound. At the most fundamental level of physical description, the quantum gravity level, where we're trying to describe the universe as a whole, time may not exist. Now you might say, but we clearly experience time. I'm watching this video right now. Time is passing. How can time not exist at the fundamental level? And here's where it gets beautiful. Some physicists, Carlo Rovelli, Julian Barber, and others, have argued that time is an emergent phenomenon. It's not fundamental. It arises from something more basic, the way temperature arises from the collective motion of atoms, or the way the smooth surface of water arises from the collective behavior of vast numbers of water molecules. Temperature isn't a property of a single atom. A single atom doesn't have a temperature. Temperature is a statistical, collective, emergent property of large numbers of atoms. And maybe time is like that. Maybe time isn't a property of the fundamental universe. Maybe it's what happens when you have complex systems, entanglement, thermodynamics, observers, when you have something that can measure change, something that can record a past, something that can be surprised by the future. Maybe time is the universe's way of organizing information about itself. Julian Barber takes this even further. He has argued for a picture of reality he calls a Platonia, a timeless space of all possible configurations of the universe. Every possible arrangement of all the matter and energy in the universe exists as a point in this space. And what we call time, what we experience as the flow of time, is really just a path through this space of configurations where neighboring points on the path look almost identical, like consecutive frames of a film. The film doesn't move. All the frames exist simultaneously, timelessly. But if you're a creature inside one of the frames, you find in your memories a record of previous frames. You feel like you're moving. You feel like time is passing. But maybe nothing is moving. Maybe there is no time. Maybe it's all just there. This is a radical idea. I'm not telling you it's correct, but I'm telling you that serious physicists take it seriously because the mathematics seems to point toward it. Now let me bring in one more thing, quantum mechanics itself. In quantum mechanics, the standard picture, the Copenhagen interpretation, says that a quantum system exists in a superposition of states until it's measured, at which point the wave function collapses and you get a definite result. The cat is both alive and dead until you open the box, and then it's one or the other. But this collapse, this moment of measurement, this now, where the definite outcome gets selected, introduces a special moment in time. It seems to require a present, a when the measurement happens. And this sits uncomfortably with relativity, where there is no universal now. Then there's the many worlds interpretation, proposed by Hugh Everett in 1957. In many worlds, there is no collapse. The wave function never collapses. Instead, at every quantum branching, every time a measurement could give one of several results, the universe splits. All outcomes happen in different branches of the wave function. The cat is alive in one branch, dead in another, and both branches are equally real. In many worlds, time has a very different character. The branching structure of the wave function defines a kind of tree-like temporal order. Branches split but never merge. But the branches themselves are all equally real. Every moment that ever could happen in every branch exists in the wave function. The universe, in many worlds, is a vast, timeless object, the complete wave function of everything with all its branches, and what we call time is the experience of moving along one particular branch. Are you starting to see the pattern? Relativity tells us that time is not absolute. It depends on the observer. Thermodynamics tells us that the direction of time depends on a single unexplained initial condition. Quantum gravity tells us that at the most fundamental level, time may not appear in the equations at all, and some of our best interpretations of quantum mechanics suggest that all moments, past, present, future, exist simultaneously in the wave function. So what is time? Here's my honest answer. I don't know, and anyone who tells you they do know is overconfident. But here's what I think we can say. The simple, naive picture, time as a universal river flowing from past to future, carrying all of us along with it at the same rate. That picture is almost certainly wrong. The physics has demolished it very decisively at multiple levels. What we seem to have instead is something far stranger and far more interesting. Time might be emergent, arising from more fundamental timeless structures. Time might be local, existing only relative to particular observers in their environments. Time might be an artifact, a way that complex information processing systems like us organize the correlations we observe between events. There's a beautiful idea that some physicists have pursued related to quantum entanglement. When two quantum systems are entangled, they are correlated in a way that transcends space. Measuring one instantly tells you something about the other, regardless of distance. And there's a fascinating suggestion from work by Don Page, William Wooters, and more recently others like Seth Lloyd, that time itself might emerge from entanglement. The idea is this: the universe as a whole, at the quantum level, is in a timeless state. But when you divide it into subsystems, when you look at one part of the universe relative to another, correlations emerge. One subsystem can serve as a clock for another. Change, which looks like the passage of time, emerges from the correlations between entangled subsystems. In this picture, you are a subsystem of the universe. Your brain is entangled with the rest of the world in enormously complicated ways. The correlations between your internal states and the external world create what you experience as the flow of time. But at the most fundamental level, from the perspective of the universe as a whole, nothing is happening. Everything just is. The present moment, this moment right now, might be the entire universe seen from a particular angle. I find that extraordinary. And I think the right response to it is not despair or confusion, but genuine open-eyed wonder. Because look at what physics has accomplished. Starting from simple observations, billiard balls, falling apples, light from the sun, we have followed the mathematics to places so strange, so counterintuitive, so far from ordinary human experience, that they challenge the most basic categories with which we interpret existence. Space is curved. Time is local. The universe may be fundamentally timeless. The past and the future may exist just as much as the present. And our experience of moving through time may be something the universe is doing to us or something we are doing to ourselves rather than something the universe is doing at all. Here's the thing I want to leave you with. In science, the deepest questions are the ones that don't have easy answers, the questions that are still genuinely open, where smart people disagree, where the mathematics is pointing somewhere we don't fully understand. Those are the interesting questions. Those are the questions worth asking. And what is time is one of them. It's not settled. It's not closed. It's not a matter of waiting for a textbook to come out with the answer. This is the frontier, the actual edge of human knowledge, where physics and philosophy and mathematics all meet, and none of them has the whole picture. And I think that's wonderful. I think the fact that we can ask, what if time isn't real, and find that the question has real, serious mathematical weight, that it's not just a philosophical puzzle, but a genuine open problem in fundamental physics, and I think that says something extraordinary about how deep this rabbit hole goes. Newton thought time was simple, absolute, universal, a stage on which the drama of physics played out. Einstein showed us the stage was curved, and the quantum gravity people are now suggesting maybe there's no stage at all. Maybe the drama is the stage. Maybe the actors are the set. Maybe everything we thought we knew about when we are is a beautiful, useful, deeply limited illusion that serves us well in our everyday lives, but dissolves completely when we look at the universe from far enough away. I don't know if time is real, but I know that asking the question seriously, following it wherever the physics leads, without flinching, without retreating to comfortable answers, is exactly what science is supposed to do. So the next time you feel time passing, the next time you look at a clock and feel the minutes ticking forward, remember that what you're experiencing may be the most personal, most local, most beautifully constructed fiction in the universe. Or it might be the only thing that's truly real. We're still working on it. And I think that's the best possible place to be.